So thank you very much, Ludmil, and thank you for the opportunity to give this talk here to the organizers. So I'm going to start reminding you of the absolute fundamentals of quantization. So as you know, but I just let me remind you. So in quantum mechanics, the classical phase space is replaced by Hilbert space. And the unit vectors in this Hilbert space represents the states of the space. And there is a process that we want that quantizes observables into operators that are acting on this Hilbert space. So I've denoted it with a hat here, as physicists usually do. And then the target of this is typically densely defined unbounded operators that acts on H. They're formally self-adjoint. And then there is the set of Dirac axioms that says that, well, the hat operation should be linear. It should take the constant function 1 to the identity operator on the space. And also, very restrictively, we want that the Poisson bracket goes to the commutator. I'll come back to that quite a bit. But the nice thing about this is that if you have this process here, then the time evolution of the system is very neatly described. If you have the classical Hamiltonian H, well then this evolution equation you see in the middle here simply gives you the evolution of the system. So that gives you the time evolution. And then, of course, there's something that we do not discuss so much, but of course, in the end of a quantum experiment, what you want to do is make some observation. And so what you can observe about these observables are the eigenvalues of these operators. So, of course, these are the ones for which there exists a vector such that f hat applied to the vector is lambda times the vector. And then there is a certain probability for observing this thing, so it's a stochastic process, right? And to observe lambda, there is a certain probability, and I've written the formula for what the probability is right there. And so another really strange thing about quantum mechanics, right, is that after you have measured this thing, well, then the state will collapse into what you measured, so the eigenvector that you measured the corresponding eigenvalue. I don't think we really understand this, okay, this part. But 130 years of experiments in quantum labs all over the world, all is consistent with this. Okay. So let me just try to remind you what canonical quantization is. So how is this process normally done? Well, you look at classical phase space, just flat space. So that's a cotangent space to Rn. So that's R2n. And then we proceed as follows. In canonical quantization, we take L2 of half the space, so L2 of Rn. And then we make the following construction. So Q hat is simply multiplication by Q, and P hat is simply minus IH bar, and then differentiation with respect to Q. And so that gives you the canonical commutation relation, so these two. And you can extend this in various ways, and now there are many choices to be had. But one way you can do it is that if you look at functions which are polynomials, sometimes you can even deal with analytic functions and the PIs with coefficients and smooth functions on X, well, then you can make the following assignment that you see right here. So you push all the P's to the right and all the Q's to the left in this process, and you quantize like that. So that's just one choice that you can make. And that gives you canonical quantization. If you apply that to the standard Hamiltonian, which is kinetic energy plus potential energy, you will recover, of course, the Schrödinger equation as the evolution equation I just showed before. Okay, there is another way of doing this, which is an equivalent way of doing this. This is, due to the work of Bachmann. What you can do is instead of choosing half functions of half the variables, you can also simply say, okay, R2n is also Cn. So you introduce a complex structure on the phase space. Now the Hilbert space becomes holomorphic functions on Cn, which is, has this norm you see up there bounded. And then you have quantum operators A hat and A hat dagger. These are creation and annihilation operators as you see them right there. They satisfy also these canonical commutation relations. And the two processes are equivalent. So if you consider a unitary transformation between the two Hilbert spaces given by the Bachmann transformation, which I have written out explicitly here, then what happens is that if you look at the QIs, then they will go over to this combination of the AI, of the A hats and A hat daggers, and corresponding the P hats will go over like this. So this is perfect correspondence of the two. Okay, now if you want to try to understand how this is related to deformation quantization, there is a really beautiful and explicit answer to this. Namely, you want to consider the Weil transform. So the Weil transform is a specific way of quantizing, yet another way of quantizing. And so the Weil transform is written explicitly up here. So you see this operator valued integration right here, where I have taken first the Fourier transform of the function, and then I stick that into this explicit expression here. And so that gives me the Weil transform from smooth functions. Of course, you know, there are conditions on when this really is convergent over to these operators on the Hilbert space that I mentioned before. And the nice thing about this Weil transform is exactly that it takes the Moyal star product to the product of operators. And what is very common in physics to use when you discuss these quantum systems to try to understand what's going on is indeed the inverse of this. And so the inverse of this here, W inverse from operators to smooth functions, of course there are conditions for when this is defined, but whatever is defined, this is simply known as the Wigner symbol. And most of quantum mechanics intuition comes from understanding these Wigner symbols and how they behave and so on. Okay, now let me just remind you, what is the Moyal product? And so it can be really nicely given like this. So you want to define bidifferential operators acting on functions on Rn. And the way you do it is first you introduce a differential operator that acts on functions on the double of the space. So functions of R2n. And so you look at P twiddle, which is this explicitly given operator here, which acts on R4n. And so that you can take to any power, of course. And so what you can do is you can define PR, so without the twiddle, to be take the rth power of this P twiddle, take two functions from R2n, pull them back via the two different projections, and then multiply them, and then let them act by this rth power of this operator, and then restrict it to the diagonal. And so that's the PR that goes from the product to a single copy of the smooth functions on R2n. Okay, and so when you apply, so that gives you a whole series of operators parameterized by R, and now you can make the generating function of these. And so actually, by definition, the Moyal star product is simply the generating series with these explicit coefficients here of those operators. And there is a corresponding nice guy, which is the normal order star product, which I've written over on the right. That is in the complex world. So where I have, you know, gone to this complex structure, so make the isomorphism between R to the 2n and Cn, as I showed you before. And in fact, those two are completely equivalent. There is this equivalence transformation T here, and that takes the normal ordering to the Moyal product. So all of this is completely consistent and nice, and you have on one side two different quantizations with Hilbert spaces and everything, and then you have the corresponding deformation quantizations and equivalences between them, and equivalences between the representations also. Okay, so of course that brings me to one of Maxime's very big theorems, so let me just try to recall it for you. Let us start now with a general Poisson manifold. So then a star product on such a general Poisson manifold is simply a product on series of smooth functions on M. And of course you can, for two functions that are just smooth functions, write out the generating series like this. And then you require that, very importantly, this product is associative. Also, that if you star multiply by 1 from the left or the right, you get just the function back. And also, if you look at two smooth functions, what you want to do is you want to look at the star commutator and see that that starts with the Poisson bracket. So that translates into just saying that C1 of Fg minus C1 of Gf is twice the Poisson bracket. And so the famous theorem by...
lambda to the power r.
And there is a lambda to the power r. That's right, thank you. And so the famous theorem due to you is that any Poisson manifold has a star product. And so it was a combination of two things. It was Kontsevich formality theorem and then Kontsevich's explicit formula for a star product associated to any Poisson structure on Rm that allowed him to show this. But in this talk here, what I want to do is really come back to this setup here, which is really what people are working with when they work in the quantum labs. And so here you see that the Hilbert space is super, super important because it's the one that gives rise to these eigenvalues and probabilities that you can measure and that you need to predict in the laboratory. And therefore, it's sort of not enough to really do deformation quantization. You actually have to somehow also understand how do they act on various representations and what are the analytic properties of this. So that's what I'm now going to take as motivation for going into the following. So now I'm going to consider a general symplectic manifold. So I'll restrict to symplectic manifolds and I'm not able to deal with the general Poisson manifolds. But I'm going to assume that we have a symplectic manifold. So we have a symplectic 2 form that's closed and non-degenerate. And I'm going to first assume that we have a certain quantization condition. And I'm going to keep with the notation h bar to begin with. So the quantization condition is that if you take the cohomology class of omega and divide by h bar, then that lies in the image of the integer second cohomology inside the real cohomology. Because if you have that assumption, what happens is that there exists a line bundle LH over M with a Hermitian structure and a compatible Hermitian connection in such a way that the curvature is minus I divided by h bar omega. Okay. And then, of course, I can now take the pre-quantum Hilbert space, which is just all L2 sections over this, over M of this line bundle. And so I'm going to call that the pre-quantum Hilbert space. Now, the reason why I want to look at this is because I can actually get quite far with Dirac's axioms in that case. And so it's completely well known, right? So if I look at the pre-quantum operators, which is A, I look at the multiplication by F on sections of L, and then I add minus I h bar nabla and then apply it to the Hamiltonian vector field associated to F. Then these operators act on smooth sections of this. And so they become unbounded operators, formally self-adjoint on L2 of M, LH. And really nicely, in fact, they satisfy on the nose, that's how actually they're constructed in a sense, the Dirac axioms. So hat is linear, hat takes 1 to 1, and it also satisfies this very stringent condition of taking the Poisson bracket straight over. But of course, this quantization suffers from several sort of problems. It is completely non-natural, and here I mean natural in the sense of it doesn't fit quantum mechanics in nature. So one, it does not reproduce canonical quantization if you take M to be R2n. Two, it contradicts Heisenberg's uncertainty principle. So no good. And we know basically what the answer is, right? We have to choose, well, let me go back. You have to choose what's called a polarization on M. Okay, so let us try to do that. And one really convenient thing to do is to actually choose a Kahler structure. And I want to mention here that any symplectic manifold has an almost complex structure. Not every symplectic manifold has a Kahler structure. I think the first examples are due to Thurston of this type. But I'm going to assume that I have a Kahler structure. That makes life simpler. I don't really think it's an essential ingredient, but everything becomes much more complicated if you don't, but probably it should be able to be pushed through in that case too. But let me absolutely assume that it is integrable. So I'm going to assume that I'm given an explicit complex structure. So that's an endomorphism of the tangent bundle. It squares to minus the identity. It leaves omega invariant, and it's integrable. So in that case, I can define a Riemannian metric on the manifold. And you know, I'm going to assume that that's a positive definite Riemannian metric. So it's a Riemannian manifold together with being a complex manifold. So and it's all in harmony, so it's a Kahler manifold. And so on such a Kahler manifold, I can take the line bundle, I can take the 0, 1 part of the connection, and that will give me a subspace of holomorphic sections. So I simply just define the holomorphic sections to be the ones for which the nabla 0, 1 in this line bundle annihilates the section. So that gives me a subspace, and I can, of course, endow it with an inner product and a norm, if I want, as you see it's written here at the bottom. So you just integrate over M, you know, the norm from the line bundle against the canonical volume form that this has. Okay, all right. Now, what are the sort of big open problems with this? Well, the open problems are, one, how does this depend on I? Okay. Will I get different answers and so on if I vary I? How, you know, what should we really choose as the pre-Hilbert space structure? So what should the inner product be? I gave you an explicit one here, but who knows if that's really the right one for physics on this curved phase space? And second of all, how do we quantize observables in this situation? So these have been, you know, questions that people in geometric quantization has battled with for many years now, because it really hasn't been a complete construction. Okay, so you know, what is really the question to the first, or what is really the answer to the first question? So for many years, I have heard many people say it should be independent of I. Okay? And so our experience from flat space kind of shows this. Remember, I took canonical quantization and I took the Bachmann version, and I show that these are isomorphic, right? So it doesn't really matter whether I take a real polarization, the complex polarization should be the same. And in fact, also we know that if you take all possible linear complex structures on R2n, they all give isomorphic quantizations. But is this a phenomenon that has to persist, or should we bend with that? Okay. So I think that's an interesting question that I'll try to shed some light on now, correspondingly with the others. But so what I want to do for the rest of this talk is provide answers for a general Kahler manifold on a general symplectic manifold. So no compact assumptions. Okay. I'll say something special about compact manifolds in the middle of the talk, but a priori no compactness assumptions, just a general symplectic manifold. So it could be, for example, R2n.
Yeah, do I remember correctly that this old paper by Gatt and Ronsley, they consider tensor powers and reproduce maxims, whatever, symplectic quantization, not maxims, but just a quantization, just a star product?
Yeah, they did something in the cases where you make strong assumptions on, you know, make very special assumptions on the Kahler structure. So, not in general. But what I want to try to do now is to try to address this problem of quantizing observables first. Okay, so let's just try to see. So let us start with the prequantum operator, which we had from before. Now, of course, it does not preserve holomorphicity, right? I mean, if I just try to apply it and I, you know, compute the nabla 0, 1 on that, well, it goes pretty good for the first part, because that's sort of almost the way it's set up. But actually, it is true. For the first part, as you see right here, so I'm just commuting nabla 0, 1 past, right? So the first part you see actually vanishes, okay, by the very definition of the, so there is a little x prime here that I can insert because the 0, 1 part of the vector field acts trivially on holomorphic sections, so I can put a prime there, and then this all completely vanishes, the first part, and then I'm left with the second part. Because, of course, the Hamiltonian vector field in general will not, even the 0, 1 part of it, so if I put a prime there, will not be 0. It's not a holomorphic vector field, right? So it will not, the bar operator applied to it will be non-zero. So therefore, you know, of course, that's not the answer. It would have been a very short talk somehow. But what I want to try to do now is to add more terms to that series. And so what I'm going to try to do is adding higher and higher order operators to this. So I have a 0 order operator and a first order operator already. So now I'm just going to add a second order operator, third order operator, and so on and continue. And so they will have their symbols. These will be symmetric tensors. So, sorry, there's a typo mistake here. T sigma is supposed to give you the holomorphic tangent bundle. There's a reason for sigma that will be clear in 25 slides. But for now, just ignore the sigma. So I would like to have symmetric tensors of increasing degrees, L. And what I'm going to do is I can certainly define a certain operator associated to higher symbols simply by making the following iterative formula that you see at the bottom here. This is a linear assignment to tensors. It's constructed exactly to be so by this correction term you see right here. Okay, so that's great. That means I just have to somehow find these G's in such a way that this operator preserves holomorphicity. So that's now the game. Try to do that. Okay, so, well, let's just simply try to take nabla 01 and apply it to this series. Let us work formally to begin with. So I'm going to move the d-bar operator inside the sum, and I'm going to apply it to each term. Now, if I apply it to each term, so it's not very difficult, but rather tedious to prove the following proposition, namely that there is a nice formula for what happens when you do this. So there exist unique sections of these Hom bundles you see right here. So A up n lower j, which is a section of this particular Hom bundle, in such a way that if I apply the d-bar operator to nabla L, GL, then what you will get is, first of all, you will get something that is of the same order where you have applied the d-bar operator to the symbol G. Then you get something that has to do with the curvature of the line bundle there. And then the rest is something that involves the curvature of the manifold. So there is a nice formula like this. I'm going to give you explicit formula for these guys in a second. And now the point is that, okay, great. Therefore, that will allow me to give a system of equations on the G's, which I can attempt to try to solve. So the system will be actually the first system here. So notice that this index on G, right, the L index, it starts with 0 order first. So we all know already what the 0 order should be. So this is actually just F. So when I apply the d-bar operator to F, I should get I omega contracted with the vector field. So I know how to solve the first one. We just discussed it, right? This is the Hamiltonian vector field that's going to go in there. But then there are more complicated equations for the higher guys. Okay, now here are the exact formulae for these A and J's. First, I give you recursive formulae. So first of all, R here is the Riemann tensor. Okay, so that's a 1-1 form with values and endomorphisms on a Kahler manifold, right? And so there is a whole stack of recursive relations you can prove about these. And then you can actually write down very explicitly solutions to these equations. So the first guy, so the one that has a 1 at the bottom, AN1, it is simply just some specific combination of sticking in the curvature of the symmetric tensor bundles. So it's like this, okay? And then you see the next guy where you have a 2 at the bottom. It has a derivative on the curvature. And then they just start growing number of derivatives until you get to the very last one, which has the maximum number of derivatives, which is n-2 derivatives on the curvature, like this. So there are completely explicit formulae for these. And so the point is now that we want to try to take these explicit formulae and stick them into this and try to see if we can solve these equations. They're sort of, and you look at them from this point of view, they're no way sort of obvious you can solve them because, you know, GL involves all the higher G's, right? So in a sense, that's not really good for a recursive system. Okay. All right. So these were the formulae. So I don't imagine you will remember those, but maybe remember a little bit about them. So now let's try to look at this. Well, the first exercise we can do is a little simple check. If these equations are satisfied, and you compute the d-bar operator of this, and you work formally, so you move the d-bar operator inside, then you apply the formulae from before, then you reorganize the terms, then you see exactly the relations up there, and you get 0. So the setup is right, formally. Okay, and so this is most likely not going to work for all functions. So I'm going to define a subspace of functions for which this works. And then I will start saying something about this subspace. So I'm going to define OK to be the quantizable observables. So these are observables for which these g's here can be solved, and for which this is all summable, and for which these f hat really induces an operator on holomorphic sections. Okay. So now let's try to experiment a little bit with it. So as we've seen before, we can start. It's very easy to start. The first guy is f. The second guy is just the 1, 0 part of the Hamiltonian vector field of f. Great, done. Now comes the rest of it. And it turns out that a smart way to try to start solving this is to actually count the number of times you encounter a curvature, or you encounter a curvature with a derivative. And if you encounter a curvature with a derivative, you count them both. So degree of curvature is 1, degree of curvature differentiated once is 2, and so on. So you just start counting number of degrees that the curvature enters into the formula. And so if you do this, you will be led to simply say, I am going to formally introduce a variable s in this equation here. So I'm going to change the equation. But I noticed that at s equals to 1, I'm back to the old equation. So I'm going to sort of stratify the whole thing like this, and then I'm going to take an s dependence on each of the GLFs to be, just a generating function for them in terms of s's, powers of s's. And so what I see immediately, since I've solved the two first ones, the higher guys for r equals to 1 and 2 and so on is 0 for the cases of 0 and 1 for L. So it only starts at the second order upwards. Okay, and now if I do this and collect coefficients of powers of s, then I will arrive at the equation you see here at the bottom. Okay, let me copy that to the next page. In fact, let me do a little bit more. You see, here you see omega, but omega is invertible. So I can multiply through by omega inverse and isolate this guy here. So I'm going to do that. So that's what I have up here. I said that omega is invertible. So now I can isolate GL plus 1 comma R on that side. And then I have stuff on the right. And what you see about the stuff on the right is that if you look at the sum of L, the indices L and R, and sum them, then the stuff on the right is 1 less than the stuff on the left. Right? Because the first term it's L plus R, that's L plus R, but over there there's L plus R plus 1. And if you sum those two, L plus M plus R minus M, it's also just L plus R. So that means there is actually a recursion for these guys in terms of the variable L plus R. Great, because now we can recursively solve the whole system this way. Now, if you look at the special case of R equals to 0, so let's try to solve that one first. If you do that, then I want to go back to, well, sorry, you just look at the equation up here. So if R is 0, you see that the last sum is not there. So you're just having that G of L plus 1 is just this operator here applied to G of L. So that's a very simple recursion, right? That means I can just solve it immediately. It means that you see it right in the middle here, and then of course it just, I go all the way down where I know what it starts with. It starts with F, so therefore that is just exactly this expression here. So I can just write out explicit solution in that case here for the zero order term. And in fact, if R is 0, that's the solution. Because I remind you that if you go back here, you see all of this is only turned on if R is turned on. If I turn off R, all of this space is 0, is equal to 0. So there is nothing more in, where do I go? Oops. There's nothing more in this recursive scheme at all if R is 0, so I simply just get the solution here. Okay. But so that is for R equals to 0, that's flat space. But in fact, very nicely, if you get this formula here, and if you go and check, this recovers canonical quantization on the nose. And so the only thing that I did was to start with the pre-quantization, add more stuff such that it preserves holomorphicity, and I automatically get canonical quantization. Okay. So now let's try to turn on R. So now let's try to, sorry, I went backwards, that was a mistake. So now let's try to turn on R. So let's make R equals to 1. So if you take the recursive relation at the top and make R equals to 1, there's only one term in the sum to the right. And so you get the equation you see in the middle. So it has a friend from before, but then it has this extra A1. But remember, A1 is just contracting with the curvature. And so therefore, I can easily solve this recursion here, because either I go with the first term or I go with the second when I'm applying the recursion. So therefore, the recursion gives me this explicit expression in terms of R. So I can write down what it is, and you see the curvature tensor entering completely explicitly in this formula here, right? And so what happens is that I get that F hat will be canonical quantization plus a correction term that involves the Riemann curvature of the space. And then it goes on, so I didn't write out the explicit one, but you know, it's very easy to understand. So one thing you could imagine is, suppose you're on a homogeneous space or a quotient of a homogeneous space, so the curvature tensor is covariant constant. In that case, there is nothing more up there. Just let's go back and have a look. So if I go back to these equations, you see if I'm saying that the curvature tensor is covariant constant, everything drops out except for the guy with a lower 1 on it. So go forward again here. So in fact, what happens in general, I can easily compute what happens in general here. What will happen is that the correction from this will be successively more and more R's that are stuck in here in this whole product. So you just stick in 2, stick in 3, stick in 4, and that's going to increase the power of S. So I just get a power series in S where the coefficients are sticking in more and more R's. So it's clear what, in fact, you can see here I keep pressing one, sorry. Here I have gone one step further in this recursion, but I have not assumed that the covariant derivative of R is 0. So therefore, what happens is that I will get 2 terms on the right from the sum. So R is 2 now, there are 2 terms. And I just keep solving them, and I have solved them up to second order. And so you see what I was talking about here is that you're sticking in 2 R's at various places. And then the last one is you stick in 1 derivative of R. And so notice that 1 derivative in R counts for 2, so that's S squared, and 2 R's count for 2. So that's the kind of system that you will get. And of course, there is a complete sort of solution to this whole problem by just keep going this way. Okay. All right. Well, I think I've tortured you enough with explicit formulae, so maybe I will make a simplifying assumption. It will unfortunately not completely take it away, but I'm going to, let's look at the case where R is covariant constant. Okay, it is really not necessary. I mean, you can keep going with these and so on. It just becomes extremely messy for a presentation, okay? So I have sort of simplified life a little bit and said, okay, let's assume that R is parallel. So if R is parallel, something special happens. So then there is only the things with no R and the things with R and no derivatives of R. And so then I can actually organize the whole thing in sort of a very neat way. Namely, I can introduce these maps, psi L, from Lth order tensors to L-1 order tensors times T bar star. And it's just contraction with omega in the case of 1. And the other cases is contraction with omega plus the curvature. Of course, an ik in front of omega, because that's the curvature of the line bundle. So now I'm just looking at the two curvatures that I have. One for L only, and then the one for the one where I have twisted L by symmetric powers of the tangent bundle. So then I have these nice operators here, and then I get a very simple formula for commuting the d-bar operator past. So I just get differentiating this GL plus this new map like this. And so then the G's just have to satisfy these very simple operators, and then once I have that, and once I can perform the sum, I will have something that takes holomorphic sections to itself. Okay. Well, the thing is that let's come back to this. So which functions can I actually do this for? So what are the quantizable observables? So I define this O to be the quantizable observables, meaning the ones for which I know how to solve the G's, and for which, so solving the G's is not such a hard problem. I just showed you a recursive way to solve them, so that's not a problem. But once you have them, you will have infinite series, and you have problems understanding whether they are divergent, convergent, or whatever. And so you would want somehow to be able to make sense of those sums. And then second of all, you wanted those operators then, really takes holomorphic sections to themselves, but that's not so hard. Once you know the sum makes sense, and if the sum makes sense in a way that you can move the d-bar operator inside the sum, then you're done by the way they are constructed. Okay, and so what I'm claiming is that, well, the analytic functions on M, so let's assume that M has an analytic structure, and then let's look at the smooth analytic functions. And then I'm saying that the analytic functions are inside the quantizable observables. So it's a huge amount of functions that are inside the quantizable functions. And what happens is that when you look at the assignment of operators and take their product, well then to first order in 1 over k, it will just be the product. And if you take the commutator to first order in k, it will just be the Poisson bracket. So it has this kind of right, Dirac setting, but that's just because it starts the right way, from before in pre-quantization. But now they're not exact. They're really just, first orders, much like what you have in deformation quantization, right? Okay, and it has the property that the identity goes to, one goes to the identity. So what is involved in actually doing this? Well, the proof of this really uses resurgence. Okay, so these series here turn out to be divergent. And so maybe this is why it hasn't been done before, because it seems to be absolutely obvious thing to do. It's simply to figure out what is the condition for preserving holomorphicity for higher order operators and just figure it out. So in some sense I'm a little surprised that this is not known, but somehow you might be stopped at this point if you are not willing to deal with divergent series, because this will give you divergent series. But so the nice thing is that those divergent series are not totally uncontrollable, so they are at most Chevre 1, so they are at most factorially divergent for analytic functions. And so therefore there is a possibility to apply the machinery of resurgence. Okay. So let me try real quickly to go through that machinery of resurgence, because I think many people here know it. But so just let me recall real quickly. We see a lot of divergent series in physics, right? That's a completely common thing. And there are sometimes possibilities to actually deal with these cases. So if you have some divergent power series, what you are hoping to achieve is to find some kind of open domain. In this case, I have a series which is in 1 over z. I'd like to have this open domain in such a way that it has infinity at the boundary. Then I would like to find a holomorphic function defined on D in such a way that when I take the asymptotic expansion around infinity, I get the original power series. And so sometimes this can be done, and you can apply the machinery of Borel-Laplace resummation to it if you're lucky. And I just remind you, what is the Borel transform? So the Borel transform is the linear map, which is just the extension of what it does on each of the powers of Z, like this. Here it's written for an arbitrary real power. And of course, gamma here is just the gamma function. Okay. And so the nice thing about that transform is that, you know, it's the formal inverse of the Laplace transform, right? So if you have a certain oriented contour gamma, and if you have a holomorphic function, define the Laplace transform this way, so of course you need to assume that the G has some properties such that this is a convergent integral, then what you will get is that when you apply it to these guys here, you get the inverse. So Borel is the formal inverse of the Laplace transform. And so let's start with a power series. And now let's assume that when I formally apply the Borel transform to the power series, that I get a nice function that I can extend analytically, and that it sort of has a certain specific decay along a ray, like the one you see right here in certain direction. Then you can consider, you know, this transformation here, so the composite, and, you know, if under these assumptions where it's bounded and so on, and the integrals are well defined and so on, this function here will be analytic in this space here, and it's where Poincare asymptotics will be exactly the series you started with. So it's not a general procedure, of course. There are many assumptions here, right? But if those assumptions are met, it really works nicely, and you get the answer you'd like to have. And so the nice thing about this is that this analytic functions is typically multi-valued. It has lots of really interesting jumping phenomenon. It will have certain singularities, and there will be jumping phenomenon. We cross lines from these singularities in various directions. And the Kahler's theory of resurgence provides some machinery for computing these jumps. It's probably better organized in terms of the two gentlemen that are sitting in the front row, in terms of wall crossing. So yeah, lots of things about that. Let me not go into further details about this right now. But we can, of course, try to apply it here. So what we will do is we will simply just take and apply the Borel transform to that series. So because it's factorially, at most factorially divergent, I can divide by L factorial on each of these. When I do that, that's a convergent power series. But then I have to come back, so I have to understand something about the analytic property of this thing. And I may say a little bit about that in a second. But the point is that it works nicely in this case, and you can apply the Laplace transform afterwards, and then that gives you actually this f hat. But now it actually becomes a family of multi-valued operators depending on a point in the complex plane, and it has jumping phenomenon and all kinds of interesting, nice things which you should maybe expect from, you know, quantum field theory considerations like path integral formulations of these things. So very simple quantum field theory, really just quantum mechanics, right? But so the point is that this series is resurgent, and you know, you can apply this Borel resummation and you get this series of operators that takes these holomorphic sections to themselves. So the rest of the talk, I'm going to skip the subscript set, okay? So remember that this will be on everything. Many, you know, infinite series will have to go through this process to make sense in what I now say. So, but I don't want to carry all these sets around. I mean, there are indices enough in this talk, so I just skip that one. Okay. Now, a key ingredient in understanding this is actually Toeplitz theory. So, and Toeplitz theory works the best on compact manifolds. So let me just tell you what it is on compact manifolds, although it is not restricted to compact manifolds. But let me just tell you what it is. So, in fact, I can tell you in general what it is to begin with. So, what you're going to do is you're going to look at the orthogonal projection from L2 sections of L to the K onto the holomorphic sections. And so there is a canonical inner product, right, that I introduced before. And then because f hat preserves holomorphicity formally, it will satisfy this equation here once I regularize it. And so therefore, I can apply the projection in to all of the terms. And now the nice thing about that is that once I have done that, then I can wonder what happens to if I take such a higher order a differential operator, apply it to a holomorphic section, but then project it back onto holomorphic things. And then something very special happens actually, which gives this whole thing much more regularity. And that is, there exists a unique smooth function in such a way that if you just multiply that function on, you will get the same turbulence operator. So this is a very special thing about turbulence operators. So you do not get more operators by taking differential operators and following it by projection. So therefore what happens is that f hat actually becomes a sequence of turbulence operators. And so you can be very explicit about this for the first few terms. So the first guy is just f, and the next guy is in fact the Laplace operator applied to f, and so on. So there are, 2D order differential operators applied to f that gives you FL. So there is a turbulence operator reformulation of all of this, and that is important to understand that this series really works and all of this stuff. Okay. Yeah. Okay, enough about that. Now let me come back. So that's what I wanted to say about quantization of observables. And so in the remaining 10 minutes, let me try to see if I can cover what about the variation of polarization. And so in order to do that, I'm going to assume that we have a family of polarization, not just one polarization, but I could in fact, I could consider the entire family of all Kahler structures that are compatible with the symplectic form. But to make life more finite dimensional and so on, I'm going to assume that T is a finite dimensional manifold and that T parameterizes complex structures in such a way that for every point in T, I get a Kahler manifold. Okay, that will give me a family of Hilbert spaces, subspaces of one of the same space that are all holomorphic, but now with respect to different Kahler structures, right? And so that subspace will vary as I move across the family. Okay, and so for the rest of the talk, I'm going to assume that they form a sub-bundle of this trivial bundle of C infinity sections. So it's kind of a reasonable assumption. There will be some cases where this doesn't happen. There are jumping phenomena because I'm only taking H0. So the more stable thing is actually take all the cohomology groups and so on, but I'm going to leave that aside. So I'm just going to assume that the H0s form a very nice bundle. And then what I'm going to try to do is try to see if I can find a connection in such a way that parallel transport with respect to the connection will give me isomorphisms of the Hilbert spaces. Okay. So, of course, there are a few elementary remarks. If I already have a Hermitian structure in this bundle, I can ask for the connection to be compatible with that Hermitian structure. That's written out there. Then the parallel transport will be unitaries. That would be great because that's equivalences of unitary structures, which I want, right? I could also ask that it is independent of this path in this manifold T that I choose to go parallel transport along. And if I ask that, then that's the same thing as asking either that I have a flat connection or I have a projectively flat connection. Okay, and so many people would maybe say, yeah, the natural thing to search for is that you must find a projectively flat connection in this case here. Okay, I'll come back to that in a second. Now, if you have a symmetry group that's acting on the line bundle and the symplectic manifold, and it is also acting on the space of polarizations, then of course you would like the whole construction to be gamma equivariant, and in which case you would then get, representations of a central extension of pi1 of t by gamma and blah, 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 all kinds of nice things, and that would be a unitary representation if the connection is unitary. So many nice things can be done here if you can satisfy all of this. Yeah. Okay. Now, there's something I think I want to skip here, but there is a little sort of story about just applying the Grothendieck-Riemann-Roch theorem to show that you cannot always find projectively flat connections. I mean, there are tons of examples where there are no connections that are projectively flat in these bundles. And so the Grothendieck-Riemann-Roch theorem gives you lots of obstructions on the Chern classes of these bundles for there to be a projectively flat connection. And so I've spelled them out here, and if you want to be very explicit, take the universal curve and quantize that So the prequantum bundle in that case is the canonical bundle, and if you use that, and then you will get certain relations between the kappa classes which are not satisfied. So there cannot be a projectively flat connection in that case. Okay. But now let's try to see what can we have. So let's try to see if we can find connections. And so I'm going to look at my family of complex structures. And then what I'm going to do is I'm going to take a vector field V on T, and I'm going to differentiate the complex structure. So look at the infinitesimal deformation of the complex structure. And so because I squares to minus identity, the derivative of I will anti-commute with I, and therefore the derivative with respect to the composition of the tangent bundle into the holomorphic and the anti-holomorphic part will not be completely random, it will be off diagonal. So it'll have two parts, and those are the parts that I have called VI prime and VI double prime. And so they are lying in these two tensor products. So the V decomposes into two pieces here. And so suppose T now is a complex manifold. Okay, then I can make the following definition and restriction on what I want to look at. I want that this family is holomorphic, and that simply just means that if I take the 1, 0 part of the vector field on T, differentiate I only recover the one part of the derivative of the complex structure. And correspondingly, if I take the anti-holomorphic part of the vector field on T, differentiate, I only get this other part that it splits into. This is just a fancy way of saying this is a holomorphic family of complex structures. So I can define, simply take T cross M and define a complex structure on that in such a way the whole family is a projection of, holomorphic map fibration. Okay. All right. So now what I'm going to do is I'm going to look at the trivial connection in this trivial bundle, and then I'm going to modify it by a one form with values in the endomorphisms. So that's what it says here on this slide. And so I want to try to find U given by differential operators. And of course, I want to try to find these operators in such a way that it preserves the subbundle of holomorphic sections. Okay, so it turns out that there is a little specific differential equation you can write down. That's the condition for that a connection of this form to preserve the subbundle. It's written explicitly here. You see U up there, and then the derivative of the complex structure. So the derivative of the complex structure and U has to talk together in a certain specific nice way. I'm going a little fast because there's only 5 minutes left. But many of you have actually seen me give talks about this part many times. Now, one thing that you can notice immediately is that this equation is rather trivial to solve in one half of the directions. Namely, if you look in the anti-holomorphic directions, then that derivative is of the wrong type to be contracted with a 1, 0 derivative. Therefore, that part is 0. And therefore, there is actually a very simple solution to U, namely just take U equal to be 0 in the 0, 1 direction, because the 0, 1 direction already preserves this subbundle, the way I've set it up. That means there is a d-bar operator in that bundle H. Okay, but if there is a d-bar operator, then I have a holomorphic vector bundle. So there is a construction here, that's nice. And then the thing is that if you now also have some kind of unitary structure given, well then you will get the Chern connection. But there are many questions remain about the Chern connection. Namely, what is its curvature? How do I choose this metric in such a way that it becomes projectively flat, or can I do that? Or can I do that asymptotically in first order and K, blah, blah. How do I write it in this very explicit form like I quantized operators before? And so that's what I'm now going to tell you. So I'm going to tell you exactly how to do this. I'm going to skip this slide here. I just want to remind you of the situation that Nigel Hitchin considered. So this is exactly the Hitchin situation. T is going to be a Teichmuller space of a surface, and M is going to be the moduli space of semi-stable vector bundles. And in that case, Nigel was able to actually find an explicit formula for a U in such a way that you get a projectively flat connection. And essentially what he used was that you can turn the derivative of the complex structure into a symmetric 2 tensor G. And it turns out on the moduli spaces miraculously that that thing is holomorphic. So it's a holomorphic symbol, and he used that. So he considered his integrable system. I mean, the way he proved that this is holomorphic is by realizing that these G's are part of his integrable system. And then he quantized his integrable system, much like Benigsen and Drinfeld, but now it's with respect to a twist, this line bundle twist. And this line bundle twist gives some new features in it. It doesn't give you commuting Hamiltonians, but almost commuting, blah, blah, and so on. And then he used the following 3 properties of the moduli spaces to actually find a nice connection in this case. And I'll just flash for you the formula. Here's the formula. So completely explicitly given, doesn't really matter precisely what it is, but there's some nice explicit formula. Okay. So, and here's little verification that this is all working and so on, and there's some other uniqueness and so on, so there's actually a unique connection that makes this work. Now, how good is this? I mean, how general is that assumption? Well, it turns out that G of V being holomorphic is extremely restrictive. So, for example, if you consider the universal curve of the moduli space, well, in that case, there is no room for holomorphic G, right? Because that space is 0. And it also goes well with the fact that I just said that there are no projectively flat connections in the quantization bundles for that universal curve, right? So Nigel's construction simply doesn't apply in this case here. So we have to do something different. And here is a different take on this, so just 1 minute, try to do it. Recall these maps, psi's from before. Recall the higher order operators. And so this will be sort of pictorially done now. Remember that I was making this assumption that the derivative of the curvature is 0, but I remind you that that's not really an essential assumption. But here comes the interesting thing. What you're going to do is you're going to start with a 1 form, 0-1 form on T with values and smooth functions. And now basically you repeat exactly what I was doing for quantizing observables, but now you are making an iterative process starting with that A. And so you can actually do this, and then what will happen is that you are going to get a Hitchin connection which has 0 order terms, 1st order terms, 2nd order terms, and so on. It just continues forever. And there is, and so now you don't have to solve the holomorphicity equation, you have to solve this equation, and that mirrors the fact that I didn't put it, I modified the recursion right there with the derivative of the complex structure. And so the point is, it all works really nicely. And in general, you will get a supply of Hitchin connections this way. Now, how is this tied to, I can say a little bit about that, in certain cases, it's asymptotically flat and asymptotically projectively flat and various things like this. I will skip that. But I just want to show you the Hitchin case. So if you take the Ricci potential and differentiate it and start with that as the 1 form. So Nigel started with the 2nd order term and then he went down to 1st order corrected and 0 order and correction. I'm going to start oppositely. I start with a 0 order term. And so if I start with his 0 order term, what happens when I run my recursion is that it stops at the 2nd order because this is holomorphic. But in general, this would not be holomorphic, of course. This would just be a general operator, a general symbol, not holomorphic, and the whole thing would continue. But he was very lucky it stopped at 2nd order. The point is that you can construct lots of Hitchin connections this way. You can also understand how they're compatible with Hermitian structures. And so I'm trying to propose a new scheme for quantization in which this family of complex structures is really an interesting and essential component, because this whole scheme here actually does what is the following. It makes a consistent quantization of observables with identification of quantizations with respect to different complex structures that come from a family of complex structures. And so depending on how large the family is, you will be forced to have fewer observables you can quantize, but you will get a bigger symmetry group on the system. So I'm saying that the quantization is by no means unique, and it will definitely have to be, I'll skip this. So it's not unique, it will have to specify a family of complex structures you would like to consider. That may be determined by a symmetry group that you want to have in the beginning. And then you're really somehow forced at various things. For example, I showed you can quantize all analytic functions, but that forces the family to be that single complex structure. As soon as you start enlarging that, this will drop down. There will be fewer functions that are quantizable. In fact, if you insist that I want to have the symmetry group of the entire space, namely the symplectomorphisms, then the only functions you can quantize are the constant functions, I claim. And so, yeah, this is, at least if M is compact. Anyway, congratulations, Max, and thanks for your attention.
What is the nature of the singularities in the Borel plane? Are they lying arithmetic progressions? Are they lying in the lattice? Are they dense? What can be said about that?
Yeah, I mean, it depends on the manifold in question, okay? So I would say that all of these possibilities occur. Yeah, so it all depends on this tuplets theory and, you know, stuff from that side and so on. Mm-hmm. So I don't have a good description of the singularities, I must say. I would like to have an understanding of what they are geometrically, and I don't know how to do that. Yes?
Or maybe a little comment. In fact, when you consider function just analytic, I doubt in Borel transform get big controls that it's analytical outside some little disk and it can't really continue. It should be, function should be really kind of entire. And there is, you said that general symplectomorphism can quantize, but there is, you have also conjectures that if consider like R to N and consider polynomial symplectomorphism, then it should extend value representations. So it will be automorphism of algebra and acts on Hilbert space. And
yeah, but this is the case where
it's kind of global when it have global on the complexification maps.
Yeah, so this is non-compact case.
Non-compact.
Yeah, because I'm only saying that you only get to constants if M is compact. Yeah. Mm-hmm. So I don't know what the answer is for non-compact. Maybe you have some ideas.
You cannot quantize Riemannian surfaces, quotients.
Well, I mean, I can definitely quantize Riemannian surfaces and so on. But the thing is, yeah, but all I'm saying is that all of the constructions are not compatible. I mean, all of the constructions are compatible under the appropriate assumptions. And I'm just saying, if you want the entire symplectomorphisms group to act on it. So for example, take a Riemann surface. Now take all the symplectomorphisms of that, so fixometric also. Then you will not get a quantization which is invariant under the symplectomorphism. I mean, in fact, we all know that that's the case, because that's a contradiction of the no-go theorem, right? So this is completely compatible with the no-go theorem. But this gives you a way to sort of specify a family of complex structures you want to look at. Then you will get a certain subset of observables you can quantize. It will be compatible with changing the complex structure. But by the way, I do not believe always that we should try to find a projectively flat connection. I don't get projectively flat connections. And I showed you that there's a good reason, because the Grothendieck-Riemann-Roch theorem is an obstruction to getting that. So therefore, the quantization, you know, there really is, if you take and move the space around with and make a loop in the space of complex structures, this will give you a non-trivial endomorphism of the vector space that should be there and say something. So, example, if you take a quantum lab and then you have a gravitational wave that runs through the system. So you start with flat space, then you deform the space by the gravitational wave, then it comes back to flat space. There should be a holonomy that you can observe. I do not know how, I mean, I think it's actually proportional to h bar to the third, so it's probably very hard to observe. But there should be an effect. That's what this says.
I mean, for Kahler, this Kahler quantization, can you say more or less in the case of a coadjoint orbit? If your symplectic manifold is a coadjoint orbit?
Yeah, that's a homogeneous space, and in which case, you know, the derivative of R is 0, and you write down very explicitly what the whole quantization is. You can see how the curvature affects the Schrödinger equation and so on.
Another piece of quantization would be to find states that quantize classical Lagrangians or maps that quantize correspondences.
Right.
Do you have something to say about that?
Well, I think that there is a similar statement about that. I mean, that would, for me, touch on coherent states and get it mapped to holomorphic things this way. And then you have to integrate the coherent states along the Lagrangians to get the wave functions corresponding to Lagrangians and so on. And so I think there is a similar statements about this in this Wien, that there is a whole deformation of this coherent state, because the coherent state will typically not be covariant constant. So what I skipped was that this process renders, quantization commutes with parallel transport of the Hitchin connection, which is really important because that means they're all consistent. And you would want to show that quantization Lagrangian subvarieties would be consistent with the connection construction. And that would require some kind of deformation away from the simple answer, which is integration of coherent states along the Lagrangian subvariety, by a 1/k expansion of various functions on that. And you can also write down equations for how that would go and iteratively solve them and so on. So it's a kind of similar scheme for that.
All right, let's continue with the questions for during lunch. Thank you very much again.
Thank you.